Hello, everybody. Today we are going to go over Winter Week 7, Day 1. So, for problem number 1, three friends, Aaron, Brandon, and Carson, line up to take a photo. In how many ways can we arrange them? If we call Aaron A, Brandon B, and Carson C, we can see that one possible case would be Aaron to go first, Brandon to go second in line, and then Carson to go third. There's another possibility that's Aaron goes first, Carson goes second, and then Brandon goes third. So there are also the following four cases that could be possible. For example, Brandon goes first, Carson, Aaron, and then BAC, CAB, and then CBA. So in total, we can see that there are 1, 2, 3, 4, 5, 6. In total, there are 6 cases that they could line up in. For the second question, Matthew has 4 different lollipops. He wants to choose 3 of them to give it to his brother. How many different options does he have? Okay, so for the second problem, I have 2 methods. So the first one is to list out all the possibilities. This is A, this is lollipop B, this is C, and this is D. So we can see that A, B, C, A, B, D, A, C, D, and B, C, D are all the possibilities. So there are a total of 4 cases. Okay, so another method would be to take a look at these lollipops and see that no matter what combination we choose, there is one lollipop left out. So there are 4 different lollipops that can be left out. So there is a total of 4 cases. Problem number 3, Daniel has 3 number cards, 7, 0, and 2. So how many different 3-digit numbers can Daniel form by using these 3 cards? First of all, we can see that 0 cannot be in the front, which is cannot be in hundreds place. Okay, so that means 7 and 2 need to be in the hundredths place. So we can list out the possibilities again. 7 is in the first place, and then the remaining 2 possibilities is 2, 0 or 0, 2. So that's 2 cases for what would happen if 7 is in the front. And the other case is that 2 is in the front, so that in the remaining 2 sections, the tens digit and the ones digit, we can see that the only possibilities are 0 and 7 or 7 and 0. So that's another 2 possibilities. 2 plus 2 equals 4. Nicholas has 2 different t-shirts and 3 different pants. If he needs to wear a t-shirt and a pair of pants to attend a party, how many different combinations does he have? So first of all, if we just look at this one t-shirt, we can see that there are only 3 different combinations. So that would be 3 combinations. If we look at this second t-shirt, we can see that there are also only 3 combinations. So in total, there are 6 combinations of outfits he could wear to the party. Today we will be going over Winter Week 7, Day 2. So for problem number 1, how many different 3-digit numbers can be formed by using number cards 2, 5, and 6? Here 6 can also be used as 9. So we first consider the case in which we recognize 6, first considered as a 6, and then we can find that once we write all of the cases out, that there are 1, 2, 3, 4, 5, 6 cases. So for the case in which that we take the 6 as a 6, we have 6 different cases. So the other case is that we consider it as a 9. So we have the cases 2, 5, 9, 2, 9, 5, 5, 2, 9, 5, 9, 2, 9, 5, 2, and 9, 2, 5, which is also 6 cases. So 6 plus 6 equals 12. So in this case, the answer is 12. Problem number 2, 5 people enter a room. If every 2 of them shake hands once, how many handshakes are there in total? So 5 people, we should draw a pentagon to illustrate this case. There are 5 sides, so let us call these people A, B, C, D, and E. We first look at it from A's perspective. He can go shake hands with E, D, C, and B. So we first record this. This is 4 cases. And then we look at B, and he sees that he's already shaken hands with A, and then he goes to shake hands with E, D, and C. We then go to C's perspective. We can see that he's shaking hands with A and B, so that must mean he has to shake hands with E and D. Oh, by the way, before I had forgotten to record that B had shaken 3 times, and now we can see that C has shaken 2 times. For D's perspective, the only person that he has not shaken hands with is E. So after shaking this hand, we can see that when we go to E's perspective, he has nobody else to shake hands with because they have already shaken with him. So when we add 4 plus 3 plus 2 plus 1, this gives us 10 handshakes. For problem number 3, Vivian drove from city A to city C. She wanted to visit an old friend who lives in city B that is in the midway of A and C. If there were 3 different routes from A to B and 3 different routes from B to C, how many different routes were from A to C? If we first consider this arrow, then based on that arrow, we can see that we have 3 different choices to go. So this pink arrow leads to 3 ways. If we go in the middle arrow, we can see that there are also 3 ways that we can proceed to C. So that would be 3 more ways. And for the last arrow, we can see that when we go to B, we have 3 more ways to go. That would be 3. So 3 plus 3 plus 3 is equals 9. So there are a total of 9 cases to proceed. Problem number 4, Samuel wants to use red or blue to color the word USA. If each letter has one color, in how many different ways can Samuel color the word? For example, USA and USA are 2 possible ways. We can first see that we can write it completely in red, and then we can write one letter in blue. In blue, 3 different cases for only one letter that is blue. The other case is that we have only one letter that is red. And then the final case would be that all of these letters are blue. So we can see that in total, there are 8 different possibilities. This is Winter Week 7, Day 3. For problem number 1, 4 people, A, B, C, and D, line up to take a photo. If B and C must stand next to each other in the middle, in how many different ways can we arrange them? So first of all, we can first draw a graph. Here, there are 4 spots for A, B, C, and D to line up in, because there are 4 people. B and C must be in these 2 spots because they are in the middle. So if B and C stand like this, there are 2 possibilities because A can come in front or D can come in front. If B and C switch places, then A could also be in front, D could be in the back, D could be in the front, and A could be in the back. So this is a total of 4 different cases. This is for problem number 1. For problem number 2, choose 2 different numbers from 0, 2, 3, 5, and 6 and add them up. How many different sums can we obtain? For this question, we can first see that 0 plus 2, 0 plus 2, 0 plus 3, and 0 plus 5, and 0 plus 6 are 4 different cases. This equals 2, 3, 5, and 6. Afterward, we can consider cases without 0. For example, we say 2 plus 3, this is 5. We also have 2 plus 5, this equals 7. And we have 2 plus 6, which equals 8. We also have 3 and 5, 3 and 6. So 3 plus 5 equals 8. And 3 plus 6 equals 9. The last case is 5 plus 6. So this equals 11. We can see that 2, 3, 5, 6, 7, 8, 9, and 11 are these cases. So that would be 1, 2, 3, 4, 5, 6, 7, 8 different sums. Problem number 3, Raymond wants to go to a shop to buy a drink and a dessert. If there are 3 kinds of drinks, coffee, milk tea, and hot chocolate, and there are 3 kinds of desserts, cheesecake, giant cookie, and chocolate brownie, how many different options does Roman have? Here are the drinks: coffee, milk tea, and hot chocolate. We have cheesecake, we say that's CC, giant cookie, GC, and then chocolate brownie, CB. Okay, so here we can see that if we first choose coffee, then we have 1, 2, 3 different types of drinks afterward. So we write a 3 here. We look at if we pick milk tea, then we can also have the cheesecake, giant cookie, and the 3 choices if we pick milk tea. And another drink would be the hot chocolate. Here we can choose cheesecake with hot chocolate, giant cookie with hot chocolate, and also chocolate brownie with hot chocolate. So that would be another 3. 3 plus 3 plus 3, this equals 9. So this is the number of different options that Roman could have. Problem number 4. In how many ways can we write 8 as the sum of 3 positive integers? Here the order is not important. 8. We could write that as, if we have a 6 in our choice, then we need to have 2 more ones because it asks for 3 positive integers. The other choices would be to have 8 equals 5 plus 2 plus 1, 8 equals 4 plus 2 plus 2, 8 equals 4 plus 3 plus 1, 8 equals 3 plus 3 plus 2. So in total, there are 1, 2, 3, 4, 5 different options. Winter week 7, day 4. Problem number 1. How many 3-digit whole numbers does the sum of the digit equal 25? So we can try for the smallest digit to be 6. So we need the other two digits to be the largest, and the largest two digits possible is 9 and 9. So once we add a 6 to this, we can find that this is 24, and the problem requires a 25, so this will not work. So the next larger number after 6 will be 7. So 9 plus 7, this equals 25. So these 3 digits, we can write them as 799, 979, 997, these 3 cases. Another case would be for the digits to be 9, 8, and 8. So this is one possibility. The next possibility is 898, and then 889. So this also has only 3 possibilities. So 3 plus the 3 equals 6. How many different rectangles can be formed by using 12 identical squares? 2 rectangles are considered to be the same if one can become the other by rotations. The first rectangle we can consider is one that has a width of 1 and a length of 12. Okay, so the next case would be for it to have a width of 2 and a length of 6. The final case would be for it to have a width of 3 and a length of 4. So as you can see, there are 12 identical squares in every picture I drew. Problem number 3, Louis and his brother Terry play the paper, scissors, rock game to determine whose turn to choose a movie to watch. If they play just once, how many different situations are there? For example, 2 possible situations are 1, Louis plays paper and Terry plays scissors as follows, or both of them play rock. So let us draw a graph. This is papers, scissors, rock. Papers, scissors. So let's say that this side is the one that Louis chooses to use. And this side is Terry. As you can see, there are 9 possible combinations. 1, 2, 3, 4, 5, 6, 7, 8, 9. So Terry plays paper, Louis plays paper, Terry plays scissors, Louis plays paper, Terry plays rock, and Louis plays paper, and so on. So there is a total of 9 combinations. This is problem number 4. So we can call the math books Math 1 and Math 2. We can call the history books History 1 and History 2. So these 2 math books cannot be together, and these 2 history books cannot be next to each other. So first of all, we first fix Math 1 and Math 2 so that math comes first in this line. So the history must go here and here. So history 1, history 2. The history can also switch places. So this is also a choice. So now we can switch the math because M1 and M2 are different. So math 2 goes first, and then history 1, math 1, and history 2. Now we then switch the history again, so that's math 2, and then history 2, math 1, and then history 1. So as you can see, for the cases that math comes first, there are 4 cases. So we keep that, and then we go into the cases in which history comes first. So if history comes first, then history goes here. So math must go in these 2 places for them to be separated. So if math comes here, so math 1 and math 2, this is one case. Another case is H1, M2, H2, M1. Also, now we can switch the places of history. So H2, M1, H1, M2, and then also there is H2, M2, H1, and then M1. So there is a total of 4 cases again. So 4 plus 4 equals 8. There are 8 different cases. Winter week 7, day 5. Problem number 1, how many fish will have their heads pointing towards the ring when we straighten the line? So we first start from this ring and go along the line. When we meet a head, we check it. It means that the head will be pointing at the ring. When we meet a tail, we cross because it will not be pointing at the ring. Head, check. Tail, cross. Tail, cross. Head, check. 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 Cross. Check. So there are a total of 6 checks in this picture. So there are 6 fish pointing at the ring when the line is straightened out. For problem number 2, the smallest number that can be in this 2-digit number is 3, because the largest number is 9. When 9 is added to 3, we have 12. So we have 93 or 39. Another case would be that 8 and 4. So this is another 2 case. And there's also a 5 and 7, 5 and 7, 7 and 5. And lastly, we have 6 and 6. So that's 1, 2, 3, 4, 5, 6, 7. In total, there are 7 cases. How many arrangements of 4 numbers 1, 2, 3, 4 are there so that the difference between every 2 adjacent numbers is not equal to 1? For example, the arrangement 1, 2, 3, 4 is not allowed since 1 and 2 are adjacent in this arrangement, and their difference is 2 minus 1 equals 1. The arrangement 2, 4, 3, 1 is not good either, since 4 and 3 are adjacent in this arrangement, and their difference is 1. In this question, my first instinct is that 2 and 3, they're in the middle of these 4 numbers, which means they cannot be next to 1. If we look at 2, it cannot be next to 1 or 3, which means it has to be on a side, because the only number it could be touching is 4. So we first put 2 on the side, And then 3 is the same thing. It's adjacent to 2 and 4, so that it has to be on the side. Here, the only case is 4 and 1. However, we can switch these two digits and these two digits to make another number that works. That would be 3, 1, 4, 2. So in total, there are 2 cases. For problem number 4, there are 2 adults and 3 kids in a car. We want to move 1 adult and 2 kids to another car. How many ways can we do that? So 2 adults, we can call that A1 and A2. We call the 3 kids K1, K2, and K3. There are 2 cases. First, we move this adult. That would be A1 with K1, K2, or A1, K1, K3, or A1, K2, and K3. So for adult 1 to be in this situation, there are 3 cases. The other case is that we have A2 with K1 and K2. Also, we have A2, K1, K3, and then the last case is A2, K2, and K3. So in total, there is another 3. So 3 plus 3 equals 6 ways. So for us to do that.